Today, we will be discussing about the complexity analysis. This is prepared by John Mark Poso, Grant Lawrence Plaza, and Abigail Ramos. A formal definition of an algorithm can be stated as the step-by-step instructions to solve a given problem. Algorithms can be extracted from even the most mundane of tasks, such as preparing food in one's morning routine. Traveling between places is another good example, and it can be accomplished via many ways: by flight, by bus, by train, or by bicycle. We choose from these options based on their availability and convenience to us. In computer science, multiple algorithms can be used to solve a single problem. The analysis of these algorithms helps determine which is most efficient in terms of mainly time, but also space consumed. Algorithm complexity is mostly concerned about the performance speed of an algorithm. It is defined as a function Tn, time in terms of input size n. Speed of algorithms depend on several factors, which includes processor speed, instruction set, disk speed, and compiler. In order to have a more abstract definition of the algorithm's efficiency, their complexity is typically analyzed in a asymptotic sense. Abstracting away details and determining the rate of resource usage in terms of input size is one of the fundamental ideas in computer science. This is the ideal basis for the comparison of algorithms because it is independent of a wide variety of factors, such as machine time and programming time. The following subsections describe different aspects of algorithm analysis, such as complexity notations, time and space complexities, and complexity classes. Asymptotic notations are used to classify this without the constants. The following notations are defined in terms of time, but their concepts can also be used to describe memory complexity. This time complexity is analyzed for infinitely large input sizes. Big O notation is a mathematical notation that describes the limiting behavior of a function when the argument tends towards a particular value or infinity. The big omega notation describes the lower bound of rate of growth of function. Time grows at least at the rate of this particular function. The big data notation gives the best idea of the rate of growth of the function. It gives a tight bound of both lower and upper bounds. Memory complexity analysis, also called as space complexity. Memory complexity is the measure of the amount of working storage an algorithm needs. That means how much memory is, in the worst case, is needed at any point in the algorithm. Time complexity is commonly estimated by counting the number of elementary operations performed by the algorithm. Best case in the function which performs the minimum number of steps on input data of n elements. Worst case is the function which performs the maximum number of steps on input data of size n. Average case is the function which performs an average number of steps on input data of n elements. Here shown the commonly used complexity growth rates. A complexity class is a set of problems that take a close amount of memory and time to solve. Such problems are often proven to belong to a particular class by passing it through an abstract computational model, like a Turing machine. Some of the most discussed problems in computer science involve proving the equivalence of two complexity classes, the most notable of which is the P equals NP problem. Some of the complexity classes include P, NP, and co-NP. The class P contains decision problems that are solvable in deterministic polynomial time by a Turing machine. Such problems can be solved much more efficiently than using a brute force approach, which often takes exponential time. The class NP contains decision problems that are solvable in non-deterministic polynomial time by a Turing machine, which includes those that can be solved in polynomial and exponential time. Co-NP class contains problems that have polynomial time verification for no answers. If give a solution that does not solve the problem, it is easy to verify if the solution does not work. An example problem is to determine if a number is a prime number. It is in co-NP because it is easy to check if the number is not prime, if the factors are numbers other than 1 and the number itself, then the answer is no, it is not a prime number. NP-complete problems are both NP and NP-hard. That is, at least as hard as the hardest problem in NP. NP-hard problems do not have to be an NP. NP-complete problems are interesting for three reasons. One is that while no efficient algorithms has been found for them, it has not yet been proven that no efficient algorithm can exist at all. Second, NP-completes have a property that if an efficient algorithm exists for any one of them, then an efficient algorithm exists for all of them, which makes the absence of such algorithms even more perplexing. And the third, several NP-complete problems are similar but not identical to problems for which efficient algorithms have been defined. Such small changes to the problem cause a big change in the efficiency of the solution. RP, or randomized polynomial time, is the class for which a probabilistic Turing machine exists with the following properties. If the correct answer is no, then the algorithm will definitely return a no, but if the correct answer is yes, the algorithm might return the wrong answer about half the time. If it does return yes, then the answer is definitely yes, but a no answer might be wrong. Conversely, for problems in co-RP algorithms, that produce a no is definitely no, but a yes answer might be wrong. BPP, or bounded error probabilistic polynomial time, is the class for which a probabilistic Turing machine exists with the property that on any given run of the algorithm, it has a probability of the most one-third chance of giving the wrong answer, whether the answer is yes or no. On the other hand, ZPP, or zero-error probabilistic polynomial time, has the following properties. 1. Guaranteed to run in polynomial time. 2. May return a yes or no, or I don't know answer. 3. Returns a definite yes or no answer. And 4. Returns I don't know about half the time. The classes P-space and NP-space are decision problems that can be solved by the deterministic and non-deterministic Turing machine in polynomial time, respectively, while problem in XP-space can be solved by a deterministic Turing machine in exponential time.